By mastering the intricacies of deployment, monitoring, maintenance, compliance, and collaboration, machine learning professionals can ensure that their models are robust, scalable, reliable, leading to improved performance and impact. For data scientists, understanding production ML allows them to design and train models that are accurate and production ready, which reduces the deployment time and effort. For machine learning engineers, it helps them to create efficient systems and help them adapt to changing business needs. Proficiency in production machine learning makes professionals more valuable in the job market, which will enable them to tackle complex real-world problems with confidence and contribute to organizational success. We hope that by the end of this seminar, you will have a better understanding and appreciation for production machine learning and the opportunities that it presents. If you do have any questions, you can save them towards the end of the session. There will be a Q&A session. I now invite Mr. Geetan Samaravikrama, Associate Architect at Dialog PSI, to give a brief on the Future Zone and what we do.
Thank you, Kasan. Hi, I'm Geetan. Geetan Samaravikrama from Product and Service Innovation team at Dialog. And at Dialog, we are very passionate about innovation. That's why we have this Future Zone program. And we go as Future Today, our motto. With Future Zone, we want to take the innovation that we do outside to the community. And also, we want to get community involved in coming up with these innovations. That's why we have this Future Zone program. We have this Lotus Tower facility where we showcase all our innovations. And also, we have facilities at a set of universities, 12 engineering universities, to get the community, the knowledge community, students, academics involved in coming up with new innovations. And as a part of that, we conduct a lot of knowledge building sessions because we know that all of us have knowledge, but the know-how is very important. So part of these programs is to make knowledge into know-how so that you can do actual production thing to benefit the country and the community. And so we have 12 labs at 12 leading universities, and Moroto being one of that, and one of the very earliest members in our ecosystem. So you'll get to know more about production AI from Dr. Romesh, because he was instrumental in making the Dialog AI first company. Rather than just talking about AI, he has led the implementation of AI at the production level, enriching Dialog product and services. And we want to make you all a part of this journey also, so that you can also get involved with us building good AI solutions. So with that, probably I think we can get started. Yeah, again, I will welcome you all of the people who came here, and also the people who join online through various channels. Yeah, thank you very much.
Thanks, Ketan. So, good morning, everybody. Yeah, I'm really happy that I've got the chance to give this talk today. This is something I've been talking about for years. I think I've been talking to Professor Karnananda about this problem that we've been having in Sri Lanka, which is what we have is the use of AI in universities is phenomenal in Sri Lankan universities. We did a recent survey, I think through SLASCOM and SLY, and about 60% of all computer science engineering projects in Sri Lanka have some sort of machine learning and AI component now. So the academic community in Sri Lanka has done a wonderful job in bringing awareness, bringing knowledge to students. But the unfortunate thing is that when you look in the Sri Lankan society, there's almost no AI solutions that have been developed in Sri Lanka out there in society. If you look at what the banks are using, the apps that we see out there, the only AI that's being used in Sri Lanka at the moment is AI that's been built abroad by the Googles and the Amazons and people like that. But there's really no local AI solutions that have been built that have gone to the people, which is accessible to the people. And that's really, really disappointing when you think of all the work that's going on in universities, all the products, all the projects that have been going on. That really hasn't been happening in Sri Lanka. And after analyzing this, what we realize is that what's really lacking in Sri Lanka is the knowledge of how to take the systems, the projects that you do in university, the models that you build, how to take it into production. Let me explain what that means. A machine learning model, all of you all, you all download a data set from Kaggle, you all find a model, you all go into SciPy, you go into TensorFlow, something like that, you train the model, you get it up to a certain accuracy level. And then the problem is that you all stop it from there. You all don't take it beyond that. But if you are to take that model and make it available to people, make it into something that's actually useful for people to use, many other things have to come into place. For the first thing, whatever model you have has to be linked onto some end user application. That could be an app, that could be a web portal, that could be a company system, an ERP system, something like that. But that's one part of taking a model into production, because that's when people get to interact with the system. They get to interact and they get to get insights, and that will help them in their day-to-day work. On the other side, a system which runs on a data set that you downloaded somewhere is once again of very little use after about a week or two after you trained, because the world is always changing. So on the other side, any model that you take into production, you have to link it to real-time data sources so that it's getting feeds from what's actually happening in the world, and then it's making decisions, giving observations on what's actually going on in the world. And then the third final one is any machine learning model over time degrades. Degrades means because the world is always changing, a model that you trained on today's data in 2 weeks' time, in 3 weeks' time, might not be relevant anymore because the world has changed. The seasons have changed, it's a different month, people's income levels, taxes have gone up, taxes have come down, everything changes. So this means that for a machine learning model to be relevant, for it to be continuously be useful, you have to keep retraining it. And it is that ecosystem that you build where you need to link it to real-time data sources, you have to link it to some sort of final end-use application, then you continuously monitor it to see when the model is degrading, and then you keep retraining it on the latest data. How to do that automatically? And that's the key here. Anybody can do this manually, but if you do this manually, it might take you weeks or months to do it manually. How to create that whole ecosystem where the system on its own knows when it has degraded and then gets an extract of the latest data and retrains itself. That whole ecosystem, building that ecosystem, is what you call production machine learning. And unless you go all that way, unless you build all those steps, really a machine learning model is nothing more than a fun project that's running on your laptop, which you can show somebody and say, I've got 95% accuracy, and you can say, cool, but it doesn't go anywhere. It doesn't go anywhere beyond that. So really, how to create these large systems now, just like now, all you guys are still very young, and you all don't know how you all probably don't have too much of an insight on how the software development industry came out. In the 60s, 70s, 80s, what we had was people were programmers. They learned how to program. But then when they took these systems out and tried to build actual end user applications, what they found was that you can build something that works, but then the problems came when you wanted to maintain it, when you want to add new features to it, when you want to extend it, when you want to fix bugs. And that's when it became a problem, where these systems are very hard to go and make any changes. It used to take weeks or months to make a change. And that held these systems back. And this is where the field of software engineering came out. The whole reason for software engineering coming out was to be able to take code that you write on a laptop and actually build an application on that. But not just an application that can be maintained and will be relevant for at least another 10, 15 years after it was built. And that's the whole idea. And then that evolved. As software became more complex, you couldn't have one programmer writing a system. What you had was now teams of programmers writing systems. And that's where, and then these systems had to be reusable. So through that, we had things like object-oriented programming, agile methods of working. All these different things came out to be able to take software, but actually take that software into applications. And this is that same revolution that is now going on in machine learning as well. Where we are trying to do is to take stuff that's running on laptops and actually build things that are useful to people. And through that, what we have is, we now have this new skill set. All you all know, we have this full stack software engineers. Full stack software engineers are not only people who write the code, but are able to build the server, the user interface, that whole ecosystem, and build the CI/CD part of it. That's what a full stack software engineer is about. And what I'm seeing is in the next 2-3 years, what we'll have is, we'll have data scientists who will build models, but more importantly, what we'll have coming into the market is full stack data scientists or full stack machine learning engineers. Machine learning engineers who know how to build this whole ecosystem and not just the data and the model part. And really, if you go into industry, this is going to be probably the most key skill that you will build and that will get you your job going forward. And in Dialog, we've been setting up this capacity. And we already have a team of about 70 people who are working on production machine learning, and we'll be growing this team to about 100, 120 over this year. But that's because that's the only way that we can manage the hundreds of use cases that we have at Dialog. So what we are doing at Dialog now is not only being able to take single use cases into production, but we are also trying to build an ecosystem where we can manage hundreds of use cases in production. And that is through reuse of software modules, reuse of models, reuse of data breaks, reuse of downstream ecosystems. We set up this concept called an AI factory, where the AI factory builds a whole bunch of reusable building blocks. So we've actually taken it to the next level, where it's not only taking single use cases into production, but how to take hundreds of use cases into production and how to manage those hundreds of use cases in an efficient way without needing thousands and thousands of staff. So today my talk is really to give you all a very, very brief introduction to production machine learning. It's a very, very vast topic, and you all can spend years mastering this. And it's a field that's continuously evolving, and every week, every month, we are seeing changes in the whole space. But what I'll do is I'll try to give you an overview of this whole space, what this all means. And at the end of this talk, you all should understand the difference between normal machine learning or data science and production data science and production machine learning, and maybe get an idea of the other skills that you all need to build around the data science skills to actually be able to build stuff that you can put out to the people. And hopefully in the next, through this batch, and it's a wonderful step taken by Moto to introduce this AI degree. No other university has done it so far. Hopefully you guys will be the first people who will start actually building applications in Sri Lanka, building applications in Sinhalese, in Tamil, which we don't really have. Because nobody has really built anything. There are enough models running in universities, but they haven't really gone out there. They haven't got into the market, and hopefully you guys will be the first people who will create these applications, Sri Lanka specific applications, through this knowledge that you all build through this. So, like I said, taking machine learning models into society is the key, whether it be a driverless car or if it's a medical diagnosis system or some sort of factory, right? Every single one of these, whether it be a driverless car, a medical diagnosis system, or a factory, what you have is at the core, you have machine learning models, right? So if you take a driverless car, obviously it's built around computer vision models, but once again, the same thing that I told you a little while ago, a computer vision model, you can train it and you can get, excellent accuracy in the lab on your laptop with some photographs that you had. But the moment you actually put it into an actual driverless car, you'll see that it's not it's not working so well because the lighting conditions change, there are objects out there which were not in your training data set. There are so many different problems that will make the performance go down. So then the moment you see that, what you have to do is you have to then identify, right, oh, this model is not recognizing trees so well, so you add some trees to your training data set and you train it again and you run it. Next time you run it, you might find, oh, it's not recognizing lampposts so well. So then you go back, you add some lampposts, you retrain it. But then, if it takes you 1 month to go from changing your data set, retraining and putting it out there, it's going to take you years to get your product ready. So what machine learning, MLOps, production machine learning does is reduce the amount of time it takes from you making a change to the model and deploying it. It's to shrink that amount of time as much as possible so that every day you can make tweaks, you can make changes, push it in. And that's, just like I'm sure all of you have heard of DevOps, CI/CD, continuous integration and continuous deployment of software. This is the next evolution when you bring in machine learning. What you have is CI/CD and CT. CT is continuous training, continuous integration and continuous deployment. And without that, without being able to do that very, very fast, it's going to take you years to be able to develop a machine learning application because machine learning applications are all about running it, seeing how it performs, going back, training your data, changing your data, training your machine learning algorithm, and then deploying it again and testing it. Once again, find what's wrong, go back, make tweaks, go back. And it's a continuous cycle. However good your model is, however advanced your model is, you're always going to be going through that cycle. And by reducing the amount of time it takes to run a single cycle is what eventually what makes it a successful or unsuccessful application. And that is the same for medical applications, same whether you're building a factory, an automated factory. Let's say you build a factory to do, QA on a garment production line. And it works really well. But then next week, your factory suddenly changes the type of clothes that it's manufacturing from t-shirts to maybe shorts or something like that. So immediately, that QA system that you built on t-shirts is not going to work. It's not going to be useful anymore because what it's got to look for is different. The fabric is different, the buttons are different, the colors are different. So then you got to retrain, you got to create a new data set, run it, and then retrain your system. And if it's going to take the data scientists 3 months to put that new QA system together for that new garment line, the factory will carry on because they can't wait 3 weeks. They can't wait 3 months until your system is ready. So that's where this whole MLOps thing comes in. How can you reduce the amount of time that you can make a change, you can improve something, and change that turnaround time? So this is just summarizes what we are doing. So production machine learning in its essence is basically the integration of machine learning systems into production systems. Production systems means systems that are actually out there in the world. Out there in the world, and just like all software, can continuously evolve and change. Now, all of you all use software all the time on your laptops, on your phones. You know that you all get minor updates all the time, where somebody's fixing a small bug or fixing a problem. They would push these bugs, push these updates all the time. And then maybe every 3 or 4 months, you would get a major update coming out where they've added a new feature, added something new. So all those things are possible. These companies are able to push out these changes so fast because their software is built on very, very strong DevOps capabilities. Using CI and CD, where their software is very well modularized. Whenever they make one change to a line of code, or they change one line of code, their automated systems will test everything, make sure everything else is working properly, and that's where the continuous integration comes in. And then the automated pipelines would package them and send it out into the application. Because even a small app now is the collection of many, many, many small packages. And changing one package can break the whole application. So before you can push it out, you need to be able to test the whole ecosystem. And that's where CI/CD comes in. So what MLOps does is production machine learning is it allows, but the problem is that you can't test machine learning systems, data science systems in the same way that you test software. It's a different way of testing. It's a different approach to using them. So What production machine learning does is it allows the integration of machine learning models into these same production systems, which requires a different approach altogether. And the goals is to create robust, scalable models that can operate in real-world environments. So that's the big change, moving away from your laptop to actually running on the real world. And now, for example, if you look at some of the systems we are developing at Dialog, we have AI systems from everything from upselling new products, recommendation systems, cross-selling products. We have churn detection. We are using AI to continuously monitor retailers and predict when certain shops are going to run out of stock, so that then immediately 2 or 3 days before those stocks can be sent to the shops. We are optimizing our logistics. So just the number of use cases we have at Dialog goes into the hundreds. And that's just, I'm just giving you an example at Dialog because I know what's going on. But this is whether you're John Keels or whether you're one of the supermarkets or one of the banks or whatever, it's the same, right? What you will have is hundreds and hundreds of potential use cases that you can deploy. But this will only be useful if you build these as production-grade machine learning system. If it's just a system that's running on somebody's laptop and you provide the output as an Excel file, not so useful. It's better than nothing, but still not so useful because you still got to have somebody manually running these all the time and changing them, and it's just too hard. That person will not be able to manage more than 1 or 2 systems on their own. But really what production machine learning gives you is the ability to have hundreds of these running at the same time. So the differences between production machine learning and normal machine learning. The goal of production machine learning is to create robust, scalable models that can operate in real-world environments, whereas normal, the standard machine learning that's followed usually is usually where you use machine learning to do some research or to develop a prototype, or maybe you're exploring new ideas. And that's the goal of what you're trying to do. But the goal of production machine learning is to take it out there, to put it out there for real people to interact with it. Production machine learning uses large and complex data sets from multiple sources, whereas a lot of the projects that you would do in university would use a single data source or a single database that you downloaded from the internet. Whereas most of the projects that we do is not just one data source, we have hundreds of data sources, and how to integrate all them together and create a single data set from that. And then in terms of model development, when we develop models, it's usually a collaboration between the data scientists, the software engineers, the machine learning engineers, and very importantly, the domain experts as well. We get business owners, people from the business units to join in on every single conversation that we have. Whereas most of the machine learning that you do would be a data scientist sitting down, trying to understand the data set and doing something with that. So it's a big difference. So this just shows you, the difference between, and I've got a unique viewpoint on this because I spent a good 10-15 years in academia as well before I moved into industry. So I've done machine learning in academia and I've done machine learning industry, and there's nothing to say that either party is right or wrong. It's just that the goals of what they're trying to achieve with what they do is different. When we do this in academia, when I developed machine learning models when I was doing research, it was more to prove a concept, to prove that this model could work, I could get to this point. And we didn't have to go anywhere beyond that because that was our goal. We had to publish a paper. But then when I got into industry, the goals changed. It was not a better goal or a worse goal, it's just a different goal. Our goals are to take things into production and to make a difference to the business that we are working with. So really, when we talk about machine learning in academia, you start with a problem definition, you prepare some training data, which is usually fixed after that. You don't change your training data much. You have your model, and then you try to improve performance as much as you can, and you get to some sort of proof of concept. And that's usually the flow that all of you probably do your final year projects on, or any project that you're working on. But when you look at the same flow in industry, we once again start with the problem definition. But right at the start, what we first define is the performance that we expect from the system. If you are developing a medical diagnosis system, the doctors will tell you, we are developing an imaging system to look at X-rays. If you can't get at least 80% accuracy, this system is useless. So always the starting point for production machine learning systems is some performance criteria. You have to get beyond this line. If not, if it's driverless car, if it can't recognize 99.9% of the objects that are on the road, it's too dangerous to put on the road. It's as simple as that. But if you're doing this in research, you will try to see how far you can go. And that's a different mindset altogether. So you start with some sort of performance criteria. Then we define the application that it's going to be worked on, that it's going to be deployed on. Is it an app? If it's a driverless car, then you got to think of IoT devices. How are you going to run your models on the car? You got to work on that ecosystem as well. Then we figure out what's the model we can use, because the model is dependent on the environment we run on. If I can run my system on the cloud, wonderful. I have enough processing power, not a problem at all. But if I need to run something on an IoT device, I can't run the biggest vision model that I have available to me. I've got to run something that can run on that particular device in the update time that I want. You can take a really big model and run it on a Raspberry Pi, but it'll take probably 2 hours to do one inference. But if you're running in a driverless car, this thing has to update itself many times a second. So then how do you get that out? So, like I said, you start with performance, you start with the application, you start with then you figure out the model that you're going to use. Then only you go and find the training data that you need to train that particular model. And then, I can't see this. Oh yeah, and then you do deployment, right? Then you do deployment, and then you do monitoring and maintenance. So you see the flow that we follow on how we do AI machine learning problem in academia and how we do this in industry is fundamentally different. It's a very, very different approach to how you define the problem and you approach the problem. And if you all go into industry and become, machine learning engineers, data scientists, this is the flow that any company is going to expect you to follow on how you develop your systems. So this is how software engineering evolved. That story I told you earlier. Software engineering evolved from the 1950s, 60s, 70s, 80s, 90s, 2000 to what it is today. And all that was based on the reason for the evolution of software engineering was the evolution of what the industry wanted from software. The industry wanted larger and larger systems. The industry wanted more complex systems, which meant that larger teams had to work together to deploy these systems. And these systems had to continuously evolve. They got to be very agile. If you have 2 apps, for example, say PickMe and Uber, and both of them have some sort of a bug because, let's say, the Sri Lankan tax rates have changed. Now, if Uber takes 3 weeks to deploy that change, but then PickMe can do that change in 1 day, means that Uber needs to shut down the app for 3 weeks until the change can be brought in. But PickMe, if they can do it in 1 day, immediately in a day they're up and running. So that's the difference between able to make a change and put it out there as soon as possible. And that's the whole point between having these agile systems, DevOps, CI/CD, all that. They all work towards reducing that time on how long it takes to deploy a particular solution. So really what we had here was the field of computer science evolved into software engineering. And that was because computer science or computer programs, algorithms had to be industrialized, had to be put into actual production systems. And that led to the development of the field of software engineering. And the software engineering is basically the application of engineering principles to computer hardware and software, usually to solve some sort of a real world problem. So similarly, what we're seeing now is AI and machine learning science, which is the application of scientific method to develop new data science, machine learning models, and training methods. By industrializing that, what we are getting is now the development of this new field, which is AI and ML engineering. This comes in many words. People call it production machine learning. MLOps is another name used for this. There's so many different names, but eventually, this is all about how to create these systems that can be deployed, machine learning systems that can go into production. And I keep stressing on this. Taking a machine learning system into production is not only about creating an app that your model is fixed onto, but it's also got to be a model that can continuously be monitored and retrained and updated all the time. And that's the crucial component. If not, in a week or two, your model is not going to be useful for anybody anymore. So what we had was, DevOps. And this is the cycle that's used in every software company around the world now, where you go through this cycle of first you build, then you code, you test, you plan, and then you deploy, right? So, sorry, you plan, you code, you build, and you test your software. Then you deploy it, and then you operate and you monitor it, and if there is any problem, you go back and you go through this cycle over and over again. And every bit of software, every update, every bug fix, every major update you see in all the software you're using on your phones, on your laptops, on AWS servers, this is the cycle that these systems go through. And the development methodologies, the software development life cycles that have been developed for this now are well known. They're called DevOps, or development operations. And this emphasizes collaboration, automation, feedback between all the different teams, because as you can see, the black part here is usually handled by the technical team, but the green part is usually handled by the business team, the people who are actually talking to the customers who know us. So it also requires these two teams to collaborate with each other. And DevOps too, over the last few years has evolved. DevOps really was coined for the first time in 2008. But in just the last 15 years, it's become probably the bedrock on which all software is developed now. And so like I said, the evolution of software and the requirements of production led to the development of DevOps. And similarly, the requirements for creating production machine learning systems has now created this new paradigm, which is production machine learning or MLOps or whatever you want to call it. And that has extended this whole cycle beyond DevOps, where you not only have the dev part and the ops part, but you also have the machine learning part which comes before that. So here what you have is, you start with the data, you build the model, you test the model, then you package it into your software, you plan, you create the software, and you keep going through this cycle. So it's a much more complex cycle that you need to go through when you're this diagram you search on Google, you'll find that. Just search for MLOps or DevOps, machine learning DevOps, this cycle is there. But this is the cycle that we at Dialog follow, or any company dealing with machine learning in production, whether it be Apple, Amazon, Google. This is the cycle that they have to go through with their software. Yeah. So this is just to show you all this as an example. So let's say you're building a image recognition application. Let's say you're building an app to say recognize diseases in plants. Right? You're building an app that can recognize fungal infections in, say, rubber plants. Right? So you build a model. Your first step would be you would go out, you would go to rubber plantations, you would take hundreds of photographs of good leaves and leaves which have been infected with different types of funguses. Then you take that data set, you come back, you sit down with an agricultural scientist, and they would tell you, oh, this is infected, this is not infected, these are the infections on these plants, and you would label your different images based on that. And then you would take some sort of vision model, YOLO or ImageNet, or whatever model out there, you would put your data in, and you would train your model, right? And that's always the starting point. And there, what you get is you have some sort of a trained model. But then if you're going to build this into an application, maybe most of the time the model will be too big to run on something like a phone, right? So then what you would normally do is, we use a cloud server where we host this model on a cloud, and we open up an API for that particular model so that people can send in images. It'll do an inference and it'll send out some sort of call on whether this is a diseased plant or not. So then the first step is to host this on some sort of a prediction server, and that's usually on a cloud server. So you've got to understand this whole cloud infrastructure as well. Then Then you got to build your app, where this could be some sort of app which is linked to the camera. You have some sort of control software where every time somebody clicks a photo, takes a photo, this photo is sent through the API onto the prediction server, and then the prediction server would have some sort of prediction. It would come back, and then the control software would show you on the app whether this was a diseased plant or not. So this, as you can see, the train model is only one part of this whole ecosystem. But then the other part that's also required is continuous monitoring. You may find that when you go to another rubber plantation, it's not detecting the ones with fungus on them. Maybe the light has changed. Maybe the color of the leaves in that plantation are different. So then what you have to do is you have to go back, take more photographs there, go back and label them, add that to your data set, retrain it, and then deploy the train model again. And this is a process that you'll be doing all the time. 6 months later, there'll be a new disease which comes up. And that disease that you were looking at earlier is no longer a problem. Once again, then you got to go back and run through this whole process. So this is just an example of even something very simple like a image recognition app, all the different components that have to come together for this to actually become useful to people. Useful to people that they can use in the real world without them having to take photos, send it to you on an email, then you put it on your hard drive, you run it through your model, you see how it is, and then you send an email back to them on what you think. That works, but it's not scalable. If you really want this to be scalable, you've got to be able to build applications that anybody can use all the time. This example is a good example because Google did a project like this in Africa, where you can try this. This model is available. It's called CropNet, CROPNET. And it's a vision model that they developed specially to detect diseases in plants. And what Google did was not only develop this model, but they actually developed an app where it was to detect diseases in cassava plantations. Cassava is, I think, manioka, right? Yeah, it's manioka, which is like the staple diet that they eat in those countries. And what they did with this app was, so any farmer could download this app for free, and they could take a photograph of their plants, and it will tell you what disease is there. But what made this app so good was it not only tells you which disease is on the plant, but it also was linked to all the different vendors who were selling pesticides and different type of fertilizers. Right from there, once you get the disease, then you get a set of options saying these are the potential fertilizers you need to use to solve this problem, and from there itself you could click a button and order it, and you get your fertilizer the next day. And it's how you create those ecosystems is how you solve problems in the real world. Building a model is great, it's nice to do, but if you really want to solve problems, you have to create ecosystems right round. And that, to solve the same problem without this app would have meant that you had to wait for some sort of agricultural technician or somebody specialized to come in, look at your plants, diagnose it, and then this person will tell you, oh, you got to order from here, then you got to go into town, order it and carry it. This would take you weeks, and by the time your plants would have died, right? But through a system like this, where you're not only just building a machine learning model, but you're solving a problem. You're solving the end-to-end problem, is really where production machine learning, the power comes in there, right? So, like I said, production machine learning system is much more than the actual machine learning code. You have the actual machine learning code part here. But to make the whole system work together, there are lots of other pieces which need to come together as well. You need to have feature extraction. You need to do process management. You need analysis tools. You need monitoring tools, server infrastructure, machine resource management, data verification, data collection, configuration, it's all that. And my experience, you all will be shocked by this, but my experience with building production machine learning systems is that the actual machine learning part of the code of a production machine learning system is about 5%, right? The rest, the 95% is all that other stuff which needs to come together to build it into the large application, to monitor it, to retrain it, all the stuff. The actual ML part where you define the model and maybe your features is very rarely more than 5 to 10%, right? So this is why production machine learning is so important. If you only focus on that 5%, then it doesn't get beyond your laptop. So this is the normal process that we follow. You all follow when you're building machine learning applications. You have a database, you do data acquisition, you prepare the data, you do model development, you train, you evaluate, and you deploy, and then you serve it and monitor it in some way. But then when you add this to the actual machine learning framework, what you have is lots of other stuff which needs to come together with this. You have the platform it's running on. It could be a cloud platform. It could be an Android platform, iOS platform, PC. If it's cloud, it could be AWS, Google Cloud Platform, Azure, or something else. Your actual application that you're building on, are you building it with Python? Are you building it with JavaScript, Node.js? There's so many other ways you can build the application. And then your actual UI UX that you interact with the user. And then at the bottom of that, as with any application, you need resource management, access control, password control, version management, library management, device orchestration. All that needs to come in. So this is where, what I told you earlier on, the concept of a full stack machine learning engineer, data scientist, is guys who can build this whole stack. And now there are people who can do this in the world, but it's still a handful of people who have the skills who can do all this. And this is the opportunity that you all have. You all can be the first full stack machine learning data scientists in Sri Lanka, because they don't exist at the moment. There are maybe 5 or 10 who are good enough who can handle all those different parts, but they don't exist still. But if all of you all think 5 years in the future, anybody who has these skills will be hired like this by any company, because this is what every company needs going forward. So, this is that MLOps diagram I showed you. So it's basically going through design, model development, and operations. And machine learning, or MLOps, is really a combination of these 3 fields between machine learning, DevOps, and data engineering. So, like I said, AI machine learning development is an iterative process where first you go through scoping, then you work on data preparation, you work on modeling, and you go on deployment. And I'll go through each one of these in some detail over the next few slides. But before I do that, any questions? I don't want this to be boring. Any questions up to this point? Feel free to ask questions, right? This is it's an opportunity for you all to learn and see, especially now that you all are just starting your careers, what are the things that you all can be looking at. This is the time to ask some questions. So, any questions up to this point? It's all clear? Okay. So what we do is, now even at Dialog, what we have is, we have defined what we call maturity levels for our system, because we can't make every system perfect. We got to go through some stages before we get it to that perfect MLOps production grade system that's continuously learning and everything on its own. So this is usually the first level of maturity that we look for. We call it MLOps level 1, where we have a data store. We do data analysis, we do data validation, data preparation, model training, model evaluation, model validation, from which we get a trained model. And then we serve this model. And this model is then opened up through some sort of like a REST API of some sort. And then we would build the app separately. And the app would access the model through the API. But then, this is how we start every single development. We start from this, where we don't try to build the whole ecosystem. We build the model, we get a model out. We take the model and we put it onto a serving. And there are lots of serving environments. There's TensorFlow serving, there's SageMaker serving. There are lots of different serving environments where you can put your model in and it'll create an API for that. And through the API, then you can make a call and it'll come out, and then it's available for anybody who has access to that API. The next level is where we call this MLOps level 2, where we have the same process, as you can see, going on top, where we define the different stages of data analysis, data validation, preparation, training, model evaluation, and model validation. But then from this whole process, what we get as output is not a model. As you can see here, what we get in here, what we get is a trained model as the output. But in the next level, what we take from this whole process when we get is not a model, but we take the source code that we use for this whole process. We take the source code that we use for data analysis, we take the source code for data validation, data preparation, model training, and all that, and we build software packages on that source code. Now, I'm sure you all can understand that this is how we do automated training and this thing once we have this process in place. So what we get here is the data analyst would, the data scientist would develop the whole experiment, but the experiment would be done in stages. But what we are getting here is not the model as output, but the code that we used to create that model. And we take the source code. We take the source code, we put it into a repository, and then we deploy it into what's called an automated pipeline. This automated pipeline is then linked to real-time data. If it's a car, it could be the cameras that you get out of the car, or phone, the images that you're getting out of the phone. It doesn't matter, right? But here, the big difference is from the earlier one is what we are deploying here is not the model, but what we are actually taking the code, and we are taking the code and putting it into a separate system where you can send in data on one side, and this will then create a trained model here. And then what we then build is some sort of performance monitoring system, which really depends on the type of use case, which whenever it sees that there's a problem in the model that's been served, it will call up a trigger, and this trigger will then take the latest bit of data and retrain the system over and over again. And that's really what it is. The big difference between machine learning in production and research-based machine learning is that the output of your development phase is not a model, but the code that you use to develop the model. And that's how you automate this whole process. And then once we bring it into full CI/CD, which is MLOps level 4, we also integrate all the the different CI/CD practices that we have as well into this system. So most companies that you would go to would have these different maturity levels, maturity 1, 2, 3, 4, where their goal is to take every system to full maturity, but they go through a process on how you go there, because if you try to target this right from day one, it can be really hard. And if the model is a failure, then you would have wasted a lot of time on building this other infrastructure. So we first make sure it's working, then only we build it up over the different maturity levels. So this is just an idea of the machine learning ecosystem at the moment, all the different tools that the different companies are producing for machine learning. And this is just from a few months ago, but now this is even larger. So this is one of the challenges of getting into production machine learning, that there are so many different tools out there, and some of them are good in some of them are not good in some, and every week there are new tools coming out. So how to keep track, how to know what's the best tool to use is a challenge even for us. We're always trying to figure out what's the best tool to use. And once you build a particular system using a particular set of tools, it's very difficult to switch to something else. That's a very, very big challenge. This, once again, the landscape, machine learning, AI, and data landscape. As you can see, it's just hundreds of different applications that are out there. So even when you all join a company and your manager or the CEO asks you, right, what's the platform you're going to build on? That's a very difficult question to answer, because putting something together is very hard, because you don't want to do, if you go back to this stage, so you see each one of these is a different stage of the whole process. You can use the same set of tools for all, but what we do usually is we use different tools for every single stage, because there are certain tools which are very, very good at data analysis. There are very, very good tools at data validation. So, for example, data analysis, something I use very often is there's this tool called TensorFlow Data Validation, which is excellent. And for data analysis, there's TensorFlow Data Analysis. That's a different tool. But then for model training, I try to use AutoML in SageMaker, and that's on Amazon platform. That's a totally different, because I think that's better than all the other ones. Then for deployment CI/CD, we use something like GitHub, but there are SageMaker has its own one as well. So like I said, we use different tools for different stages of this, just based on what we think is best for the particular this thing. But that's once again a challenge because this space is always evolving. And one of the challenges is building your software infrastructure in such a way that you can switch tools also. If something better comes up, how can you take what you had and take it out and put something in without having to change the rest of your system? That's the software engineering challenge. How you make your system modular enough that you can switch between these different systems. And that's a whole different ballgame, but that's the type of challenges that we are trying to do at Dialog at the moment, because we realize that we have to keep up with the technology that's coming in. We have to make our software more modular so you can put something out and put something in. If not, you get tied into what you started building with, and 3-4 years later, you're forced to keep using that, even though there's something better out there in the market. So that's a different one, but yeah, that's a challenge that you all will face over your careers. In terms of one of the key skills you will need as a machine learning production engineer is you need to be good on the cloud, right? I can't really tell you which one is better, but the three main cloud platforms that I would say 99% of all production machine learning systems are built on now are either on AWS, Microsoft Azure, or GCP, Google Cloud Platform. It's one of these three. They're all good in their own ways, and they each have their weaknesses. They are similar but also different. The interfaces are different, how you run them, how you create instances, the pricing is different across them. So that's once again a challenge. Now, I'm quite good at GCP. I've used GCP a lot for projects, but now when I started working at Dialog, Dialog runs their whole infrastructure on AWS. So then I had to learn AWS almost from scratch. And then there are some things now coming out, like the OpenAI GPT-3 stuff, which works best on Azure because Microsoft has a partnership with OpenAI. So now we are having to learn that because AWS doesn't have a link onto Azure. So it's, as I said, that's an ongoing challenge on how we keep up with what's going on. So now at Dialog, we are using some of AWS and we are using some of Azure for the generative AI work that we are doing with OpenAI and things like that. But yeah, I mean, like I said, they're similar but different. They each have their own certifications. You can go online, become a GCP developer, AWS developer, Azure developer, and there are different ones for data engineering, machine learning, data science, all that. So, but either way, my advice to you is at least be really good at one of these platforms, right? But that will give you the foundation, and then learning the next platform will be a lot easier. Learning the first platform is a bit hard because there's a steep learning curve. But once you know one, for example, GCP, learning AWS is not simple, but it's a lot easier because there are lots of similarities as well. So in terms of the different roles that we have, that we use in our production machine learning team, we have data engineers. Data engineers are those engineers who build the software that take data from sources and bring it to our data lake or our data warehouse so that our machine learning teams can use it. I mean, just to tell you an example, Dialog has something like 800 data sources where data in different places coming from this thing, and these data engineers build these ETL pipelines, and we have about 2,000 ETL pipelines at Dialog, which all this data is coming in real time, and the engineers who build those systems are called data engineers. So that's a very, very specialized skill and probably one of the most important skills that we have at Dialog. Then we have the data scientists, and the data scientists are usually those who look at the data, analyze the data, look at the model, try to figure out what can be done with the data. Just give me a second, I'll get some water. And then machine learning engineers are those who select the model, train the model, set the hyperparameters for the model, stuff like that. Then we also have MLOps engineers. The MLOps engineers are those who set up the whole ecosystem for CI/CD, CT. Then we have the cloud engineers who basically manage the cloud platform. That's a really, really important part for us because clouds are very, very expensive. So if the cloud engineer doesn't do their job properly, some of these instances can end up costing us hundreds of thousands of dollars. So that's a very, very specialized skill. And if you don't have a good cloud engineer, any system you build might cost more than the benefit you're getting out of it. So the cloud engineer has to be really, really good. Then, just like any software team, we have quality assurance, we have DevOps, we have software engineers to build that whole ecosystem, we have UI UX engineers, and we also have IT. So for us, even to put a very, very small project together, just to say forecast how much sales a particular shop is going to do on a particular day, all these skills have to come together. And in the future, that's why I said a full stack data scientist or a machine learning engineer will have most of these skills. And if you look at maybe the software industry a few years ago, you had different people who were doing the server, different people doing the front side, the UX, the application, all that. You had about 3 or 4 skills coming in. But now this has changed, where you have the full stack engineers coming in, where we expect people to do the whole thing, all the way from the server, all the way to the app and the user interaction. So I expect the same thing to happen within machine learning as well. And this is something that you all can watch out for. If you all were to pick some of the skills, definitely data science skills are very, very important. Data engineering, really key. Because if you don't know how to manage data, get data from one place to another place, clean it, make it available in real time, once again, your application will be hard. Machine learning engineering, obviously, because you need to know what you can do with models. And the MLOps side and the cloud engineering side. This part are the key components that we need, especially for machine learning, production machine learning. Okay. So we'll go into the, these are the four main stages for, building these machine learning systems. And every system that we build, we go through these four steps: scoping, data, modeling, and deployment. And I'll try to give you a very brief introduction for some of the things that we look at when we are going through these 4 stages. So even when you all are maybe doing your projects, you all can go through these same 4 stages. And that'll give you an idea and your first experience on how to look at something in production. So if you look at how now when we do this in all the companies I worked at, including Dialog now, everybody has different ideas on the type of things we can do, we can't do, what are the things we should be doing, things like that. So the first thing that we normally do is we brainstorm business problems. Like I said, going right back to the beginning of my talk, when we do production machine learning, we don't start with, I want to do something with computer vision. I start with, I want to solve, these retailers are costing too much money, I want to solve that. So you always start with a business problem. You don't start with a technical problem, you start with the business problem. And that's always the big difference between academia and industry. Then, once we identify a set of problems, then we look at what are the potential solutions that we can use to solve those problems. Now, for example, the retailer problem, the company may identify that we are sending too much stock to particular retailers. We are sending too many SIM cards to retailers, and then when other people want SIM cards, there aren't enough left. So there are lots of SIM cards lying in the retail outlets. So then the solution might be where we have more of a prediction on the number of sales that are going to be made at a particular retailer, say for a week, and we know how many they're going to sell. Maybe they're going to sell, we have a prediction saying they're going to sell 10 on Monday, 15 on Tuesday, 5 on Wednesday, 10 on Thursday, and 10 on Friday. That's 50. Then what we do is the Sunday before that, we send them about 60. so that they're covered for that week instead of sending them 100 every time we do a restock for them. And that allows us to optimize the amount of stock we send to the customer. And believe me, that type of system saves a company like Dialog hundreds of millions of rupees in terms of stock management. And then once we have an AI solution, we assess the feasibility and value of that potential solution. Can it actually be done? How much is this going to cost us? And is the cost, can the cost be justified to the benefit that we are getting from that system? Then we define milestones. Milestones are usually those MLOps maturity levels that I talked about earlier. And then obviously when you're talking a corporate, you have to budget for your resources. So that's always the steps that we go through. Potential questions are always, what project should we work on? And very, very importantly, and this is something I stress for all my engineers, is what are the metrics for success? And I told you this earlier as well, like let's say you're building a diagnostic system. You have to have a starting point where you say, let's say you're building a diagnostic system for X-rays, where you have to, somebody has to tell you where, this has to have at least 75% accuracy. If you don't get beyond that point, this system is not of any use. Take the driverless car example. If you build a system that's only 80% accurate, that means 1 out of 5 times it's going to crash into a tree or a person. Once again, useless, right? So any type of production system, you always have to have some sort of measurement for success. What is the minimum level of performance that you need for this to be viable, for this to be useful for people? Then what are the resources that we need? Very, very important to us right at the start. What type of processing power, what type of cloud computing resources, what type of data do I need, what are the skill sets I need, all that, and what do we finally want to achieve out of this. It's also very, very important to separate the problem from the solution, right? It may sound a bit strange, but it's very, very important to do this. You have to separate out the problem and the solution. Think of the problem you're trying to solve, and then you can have 10 different solutions or potential solutions for solving the problem. So take that retailer thing. Obviously, one of the solutions could be forecasting. But forecasting also, if you look at the number of forecasting algorithms out there, you can use FP Prophet, you can use Arinma. There are about 10, 20 different forecasting algorithms you can use. So that's the solution. But the problem is still the same: is how do I reduce the amount of stock that's held in a particular retailer? So, like that, you have these problems, which is increased conversion. That's like, recommendation systems. I want more people to buy from our website for our app or something like that. Reduce inventory, which is the one I talked about, and increase margins. But then the solutions for each one of these can be, different ones. Increased conversions could be, making your website more searchable. It could be better precision marketing or recommendation systems, hyper-personalization, cross-selling, upselling. So the problem is one, but the potential solutions can be so many different other options. So don't be fixed on one potential solution. We look at, are there 10, 20, what are all the different solutions we have? If you want to reduce inventory, like I said, same thing. Potential solutions for this, demand prediction, which is the one I talked about. Better marketing, so that even if somebody has too much stock, better marketing means they'll sell a bit more. Just in time, which is what a lot of factories use now, where what you need comes exactly like 5 minutes before they actually need it. Stock out alerting, trend, seasonality, all these things. If you want to increase your margins, cross-sell, upsell, reduce marketing costs, stuff like that. It's also very important to benchmark what you're doing, because especially if you're starting a new project, let's say you're building that example I used earlier, which is a diagnostic system on X-rays. When you start the project, you really don't know what's good or bad, right? So it may be without knowing what's good or bad, it's very difficult to set a benchmark. And so then, if you don't really have that, you may look at external sources, like you may look at research publication. This is where research is important. This is why I said that whole research process is so important, where you look at the papers and see for this type of X-ray problem where they're trying to detect a particular type of cancer, what's the best that somebody has done in the world up to this point. And then when you're building a production system, your benchmark would be at least get to that level. But if you don't have that benchmark, once again, it becomes an R&D thing where you don't know where you're going to go with this. So it's also important. So you can look at external benchmarks where you're looking at publications, papers, competitor information. Then let's say you're building a system to automate something that was previously done by humans. So take that, let's say the QA, the quality control problem in a garment factory, right? So if you go and talk to a garment factory, you will always find that those, at the moment, if it's done manually, the production line of all the T-shirts that have been completed are going down the line, and there'll be people standing on both sides who are looking for defects in the ones that are going down, buttons that are not there, stitches that are not straight. The moment they see that, they take it off the production line. But even those people are not perfect. They will make mistakes. And usually in these factories, it's about 97, 98% accuracy on how many of the ones that have a problem that they actually pick up. And so if I was building a system to automate that particular system, let's say I'm building a camera that can look on top, and then when it sees a button or a thread or something out of line, it will alert, and then somebody can take it out. But then when I'm building that system, if the performance of the humans who do that job was 97%, and if I build something that's only 90%, will the company use it? No, right? Because they're going to miss too many ones, and then they will lose money on that. So for a problem like that, where you're trying to replace a human, every benchmark, anybody who's building a system like that, their benchmark would be what's called HLP, which is human level performance. You would first establish human level performance. Same for a medical diagnostics system, right? Your benchmark would be what's the level that humans can get to now, and then means that my AI system has to get at least to that level. If not, it's better for the company just to keep having people there, because the loss of missing stuff is too great. So, which is once again, I'm trying to tell you the process that you would go through before even looking at your data, before deciding what model to use, before going through any of those, what are the decision points you need to make to set those baselines for how your system should be operating. So human level performance is something that's really useful. We use this all the time, especially when we are building automated systems. HLP is, like our mantra. If we can first find an HLP for something, a human level performance, that's always where we start. And that's the minimum performance level I would define for a system that I'm building. So this also depends on whether you're working on unstructured data or structured data. You'll know the difference between structured data and unstructured data. Structured data is data that's in tables, like banking data, insurance data, stuff like that. Unstructured data is things like images, videos, voice, things like that, which has really no structure to it. And how you would define benchmarks would be different depending on whether it's structured data or unstructured data. Unstructured data, more often than not, it's HLP, right? It's an audio. If somebody listens to a sentence, how many times would they get it 100% right? That's my benchmark, right? And that's always how we do it. Yeah, and then this is, it's getting more towards the business side, but once again, very, very important for production machine learning is bridging machine learning metrics to actual business metrics. And this is, once you get a system out into the world, now let's say I'm building what's a good example? Let's say I'm building that retailer stock prediction system. I'm building a retail stock prediction system, and obviously, just like any machine learning system, I have a training data set. I have a training data set of all the sales at all the different outlets over the last year, and I build a forecasting model which can forecast the sales for any given outlet for the next week. That's my system, and on my training set, obviously, I would then train up to maybe 2 weeks before, and my testing set would be the last 2 weeks, and I would run it, and then I would have some sort of metrics, the accuracy, the precision, the F1 score. I'll have these different metrics on how well my model is performing. But then, what you need to do then is but that once again is just a machine learning metric. It doesn't really mean anything. What you need to do is to then link that to what that actually means in the real world. So for example, you may find that by having an accuracy of 90% on my retailer score, what I would be doing is I would be improving the stock efficiency of that particular retail outlet by, say, 10%. I'm just giving you a number here. But then what I'm trying to get to here is, if I can improve my model accuracy from 90% to 91%, what does that mean for the business? By improving it from 90 to 91%, what happens to that 10% improvement that I had earlier? Is it going to go up by 1% or 2% or 3% or 4%? And those are the type of business decisions we make. My first model would be giving me 90% accuracy, which is good, but then I'm getting a 10% efficiency gain in the market. But then if I can improve that model accuracy from 90 to 91%, the efficiency gain in the retailer might go up by 2%. And the 2% might be worth 10 million rupees or something like that. So what we always try to do is whenever we build these machine learning models, is when we first run the model and train the model, what we first get is the machine learning metric. But soon as possible, what we try to do is through that, to try to link that to an actual business metric. So if you are building a recommendation system where we are trying to recommend new products for a customer, let's say, and usually a recommendation system is a regression system, something like a logistic regression system. Let's say I'm getting 80% accuracy on that. And through my 80% accuracy, let's say I'm getting something like a 5% conversion rate. You ask what's the conversion rate? Conversion rate means now if I send a marketing message to 1,000 people, 5% of those people actually take that offer and buy that product. That's called my conversion rate. So that means my model is performing at 80%, but my conversion rate is 5%. For every 1,000 emails I send, 5 people buy the products that I'm recommending. Then I find that when I worked hard, and I managed to increase my model accuracy to 85%. Then I find that my conversion rate has now gone up from 5% to 6%. So that means by improving my model performance by 5%, I was able to get an increase in conversion by 1%. And that 1% conversion might mean, say, 100 million rupees of extra sales for the company. So that's a process that we do all the time. For us, it's very, very important to link a machine learning metric to what's actually happening in the real world. And that's when we start to get the correlation. The machine learning metric on its own is really not very useful. It's a good starting point, but to actually understand what's happening in the real world, all right? Okay. So this is something that's really important, and like I said, it's something we do. It's an essential part of everything that we do to make sure that we always. Is it going off now? I said, oh, no idea, no? Okay. Do we have to go out or no? We can stay here. Okay. Cool. So this is if you all do any projects, it's very important, and that's how we make a decision. Now, let's say I was at this is getting more into the business side, which all may not be that interested, but I'll explain it anyway. So let's say I'm at 85%, And I know that a 5% improvement in my accuracy will give me a 1% improvement in conversion rate. And a 1% improvement in conversion rate is going to bring me 100 million rupees extra revenue. So now I know that if I was to invest money in increasing my accuracy to 90%, that means that my conversion rate will probably go up to 7%. So that means another extra 100 million revenue. That means I can go to my manager and say, you can spend up to 100 million, I'm going to give you your money back. So that's how you make the justification for investment in more time, more engineering time. So if you don't establish those links between the machine learning metric and the business metric, it's a very difficult conversation you have with your CEO or your CFO or your accountant. He will say, why do you want me to spend so much money? What's the return I'm going to get? And you've got to link those two together, right? So this is just once you all get into industry, this probably won't sound so important to you all now, but when you all get into industry, this will be the most important thing in your life. You got to go to your CEO or somebody and ask for money to invest in the project that you're working on, and you got to justify that cost. And the way you justify that cost is by doing this linkage. Right? Then something very important is, and we do this all the time, are the ethical considerations. Is it ethical, what we are doing with this system? Is the project creating net positive societal value? Any system is going to, harm somebody and do good for other people. But what you got to make a call on is whether the benefit is better than the bad that it is doing. And that's a call that most business managers won't understand this and they won't care. So my opinion is that this responsibility has to be taken over by the data scientists and the machine learning engineers who build these systems. They have to also consider the ethical considerations of what they're doing. Let's say you're building a credit scoring system. A credit scoring system will be used by a bank and will eventually be the determinant where the bank decides whether to give you a loan or not, right? So then those type of systems, or a visa application. Now those type of systems, it's really, really important to think of ethical considerations, because you got to look at the way the model performs and see whether it's behaving ethically. You may, and this is the type of stuff that we do all the time, especially with our credit scoring systems and things like that. Where what I look at is I run maybe 1,000 customers through the system, and then I look to see how many got rejected, how many were accepted for that particular loan application. Then I say, let's say I find that, say, 80% are being rejected and 20% are getting the loan. So I'm just picking a number here. Then what I would do is I would divide those same 1,000 customers amongst men and women. And then I would see, out of the men, what's the percentage of people who were accepted and what's the percentage who were not accepted. And then I might find that amongst men, the acceptance rate is 25% and the rejection rate is 75. But amongst women, acceptance rate is only 15 and rejection is 85. That means the model is not balanced. That means there's a bias towards men. So then I have to go back and change my model. Similarly, I may break my data up according to district. And I may find that it's giving more loans to people in Colombo and not giving loans to people outstation. Then I would look at income level. I would break it down like that. And just like that, I would keep and this is called slicing and dicing, where you slice your data according to different parameters and see whether your model is performing equally amongst all these different slices. And that's the responsibility of a data scientist, as you can understand, because the manager is never going to ask you that question. Right? He won't have that understanding. But it's the data scientist who have to set up that system to make sure, especially things like credit scoring, things that actually affect people, salary increments, things like that. You have to make sure that your systems are balanced, ethical, and fair. And that can only be verified with data. And you've got to slice and dice the way I just explained. You got to break it up and see what the accuracy levels are on those different slices. So yeah, is the project reasonably fair and free from bias? And you have to debate the ethical concerns. Let's say you're building an automated system, that factory system. which is going to do the QA, the quality control in a factory. It's really cool if you can build a system that performs better than HLP. Awesome. But then, have you had the conversation of what's going to happen to those people who are now doing the QC? What's going to happen to those people? Has the company thought about it? Are they going to be fired, or are they going to be retrained to do some other job? Has the company thought about, are they going to invest the money in doing that? So that whole 360 view of the impact of AI systems is also really important. And as data scientists, it's really good to get caught up in the technical side of things, but you also got to consider the societal and the ethical side of what you're working on as well. Because if you don't do it, nobody else is going to do it. And that's my feeling is that's a responsibility of the data scientists to also think of the impact of the things that they're working on. Yeah, so we always try to work backwards from the end, where we design the entire value chain, we blueprint the end system, design a clear project plan and milestones, and design and we work backwards from there, especially the buy-in from the business owners. So let's go to the second part of this thing, where what I talked about all was how we scope a project and how we plan a project. And so you can see the scoping part is quite tedious. We spend a lot of time on scoping these projects. But then once we know what we're going to do, what are the benchmarks for performance, all that stuff, then we move on to the second part, which is figuring out what we're going to do with the data. So I'm sure all of you all know this now, which is the quality of a machine learning system is highly dependent on the quality of the data that you use to build your system. So your primary responsibility here is to make sure that you have good data. And here what I mean by good data is going back to my earlier consideration, what I talked about ethics, right? You may be building a now, a good example was they found that, so there was a system built in the US to do criminal profiles, where people would come in, somebody would be arrested, and they would give the photo and certain whatever they know about the customer, know about the person that they arrested, the age, where they live, their income level, whether there are any previous arrests and things like that. And the system would give some sort of a prediction or a determination on whether this person should be given bail or should be kept in jail based on this thing. And I think it was in Chicago or something like that, where they started using this system. And so every time a judge or whatever, the police had to make a call on whether to be lenient or be strict with this person, they would run this person through the system. And but after a while, there was a court case put on saying that this system wasn't fair. And then some external auditors had gone into the system. And what they found was that the system was being extremely biased towards people with dark skin. They were saying keep in detention people who had dark skin more than people who had white skin. And then they had gone into the system and looked at the data. And what they found was in the training data set, 90% of the people in the data set were black. So that means immediately this assumed that if you were black, you were going to be a criminal. And this thing. So once again, this was a fault of the data scientist who built that system right at the start. He didn't make this data set balanced. So when you're building your data set, it's your responsibility to make sure that you have equal numbers of men versus women, you have equal numbers of people from the different districts, equal number of people from the different income distribution levels, whatever. But that is your responsibility, to make sure that your system is biased. Just showing that you're getting 95% accuracy is not good enough. You got to show that you're getting 95% accuracy across all these different slices. And that's what makes a good system. And that is, before you even start modeling, when you put this data set together, that's like the really, really important part of building these systems. And that's a responsibility, and that's what I mean here by good data. So covers all important segments and use cases, define consistently, has timely feedback. Another big problem, another mistake people make is that they may be using data from 2 years ago. They're not using the latest data. And then they think, oh, I'm getting 95% accuracy on that, I'm good to go. But now the world has changed. So you also got to make sure that you're using the latest data that you can possibly access and is sized appropriately. So this, another issue that we see is inconsistencies in labeling. If you're building a vision system, so you see this is the same image, which 3 people have labeled in different ways. In this one, you have a fox here. You see the boxes been drawn very, very tight to the fox. In this one, what they've done is they've drawn a box, but there is a bit of a padding, maybe about 10 pixels around the fox. And in this one, they have only drawn the face. In this one, you see the fox is partially covered. So in this first one, they have drawn a box around the fox's face. But in this second labeler, has drawn a box around where he or she thinks the fox should be as well. Now in this, you may think, for me really, it doesn't really matter which one you use. This is right, this is right, this is right. But what really matters is that you're consistent in the way you label across your whole data set. If you decide that all your boxes should be tight on an object, just make sure that every single label that you have is tight. If you're going to use padding of say 10 pixels around an object, fine. But make sure that every image is labeled like that. Similarly with the face, and these two also same example. I usually prefer this one, where I actually make an assumption of where the fox is and draw the whole thing, but even this is fine. But once again, where I've seen most vision projects fail is where there's a mixture of different labeling conventions used in your data set. And then the machine learning model gets really, really confused. So it's very, very important, especially now, this is not a problem if it's one person doing all the labeling. That's fine, because then you just stick to the same convention. But usually when you look at like driverless car projects and things like that, there are, usually you have thousands of people who are doing the labeling of this. So then one of the biggest challenges is how to make the labeling consistent across all the different labelers who are working on this. And that's where, especially if you're doing something like image labeling and you have multiple people doing labeling, it's very important for you all to, right at the start, set up a labeling convention where you all agree on a particular way you're going to label, and then you follow that from there onwards. But the biggest mistake is if you all use a mixture in a data set, once again, your model is not going to perform very well. Then you got to think of situations where you're working with small data and big data. Small data is when you have more than about 10,000 data items. Big data is when you have more than 10,000. So, and the way you approach these projects, whether you're working on small data or big data, is fundamentally different. It's a very, very different process. When you're doing small labeling, clean labeling is critical. And when you have something like 10,000, you can actually manually go and check all 10,000 yourself, and you can make sure they're right. And you can also get the labelers to talk to each other, because you may have 10, 20 labelers, they can all talk to each other. But the moment you get more than about 10,000, it becomes a lot more difficult. It's practically impossible for everybody to validate every single label that's been done. And when you have about 1,000 labelers, you can't really get them to talk to each other and sort out problems and questions. So whether you're dealing with a small data project or a big data project, the challenges and how you would put that team together is different. You can't use the same method for a small data project and a big data project. Small data projects are handled in one way. Big data projects are handled in another way. And when you start your project, you got to understand whether you're dealing with a small data or a big data project, and your conventions, protocols, processes have to be aligned accordingly. How long do you spend collecting data? This is a question I get asked quite a lot. So my rule of thumb is that you will never have enough data, right? however much you keep adding data, you will never have enough data. Uh, the way I normally approach projects is, I don't wait till I have all the data to start training a model. I start training the model as soon as I have just enough. Let's say a vision model. Let's say I'm building a like that QA system for a factory. Usually, if I have about say 100 images of every single type of defect, that's enough to start on. I'm not going to get great accuracy, but I can still get the model training. So then what I do is I collect as much data as I minimally need, and then I start training my model. And then from there, while I'm training my model and the data scientist is working on the attributes and working on, I'm still collecting data. And that data will go on. But a lot of people make the mistake of first waiting until all the data is collected, and then they start training the model. And that can usually go wrong because you may be collecting the wrong data. It's always a good step to start with your minimal amount of data, start training the model. Then while you're training the model, you're also collecting data on the side, and it's a parallel process that you go, where you're training the model and refining it while you're collecting more data as you go along. So that's usually my process, where get to training as fast as possible. Start with a small amount of data, use initial data to select the model, training algorithms, build the loop, and then add data as more data comes in to iterate it. But I like to get to actually building the model and training the model as soon as I can, without waiting for all the data to come in. And then I learn about the model, what it can, and that also gives me better insights on what type of data I should be collecting as well. So that's a bit of a process there. Then things like metadata, model provenance, those things, you probably haven't even heard of this. But metadata is data on data, right? You all know this. And especially in machine learning, this is a really, really important thing. You must know where your data came from, what was the source, who collected it, what date was it collected, when was it collected, because especially when you're going into things like checking the fairness and the bias of systems, you need to know where that data came from. And if you don't do proper cataloging of your data at the time that you're putting your data set together, when your project grows and it becomes a production grade system and a problem comes up, it will be a nightmare for you to go back and dig and find out where this problem came from. So every bit of data has to be cataloged and maintained, and all the possible metadata, who collected it, where it came from, what time was it collected, what date, what country. The more information you have about the data means that later if you have a problem, you can always go back and understand why that problem came. And that's got to be done with metadata. Then the third part, modeling. The goal of model development is to achieve or pass expected performance goals. And I talked about this a lot earlier. We talked about human level performance. We talked about the different benchmarks that we do. So in production machine learning, the research is not how far you can go with it. Your research or your development is always try to first check whether you can get to that benchmark that you defined earlier and whether you can pass it, and that's it. Whereas, like I said, in academia, when I've done research, what I try to do is I try to see how far I can push the accuracy, and that's my goal. But here, my goal is not that. My goal is to first find out whether is it possible to get to that goal that I set up, and then how do I get to that goal, and then I usually stop there, and then I go into production from there onwards. So we'll go to the last bit. So now we're talking about model development, and this is usually the steps that I follow when I'm working on a production grade system. First, like I said, the most important thing, I've been saying this over and over again, is to start with the baseline. Define a baseline for model performance. Usually benchmark against something like HLP, human level performance. This is a word that you will hear over and over again when you're talking about production machine learning. Then once you know the model performance, and the model performance usually will be given to you in terms of a real world model performance metric. You got to link this somehow to actual machine learning metrics. And what I usually do right at the start, even before I start model development, is I then define the different slices of data that I want this to perform as well. For example, the credit scoring system, I would set a benchmark for myself saying it's got to perform equally men versus women, Colombo versus outstation. And like that, but I would also establish those benchmarks for myself as well. And identify those particular classes which I would maybe look at, low income versus high income, executive workers versus non-executive workers, like that. But I would define those different slices of data that I want my system to perform as well. It's not an afterthought that I look at later, it's part of my planning process as well. Then I define whatever constraints I have, depending on what's the environment I can run, what's the can I run this on a cloud? How much money do I have on a cloud? How much how can I use a GPU, or is it too expensive to use a GPU? Do I need to use a slower processor of some sort, something like that? Then once I have all those in place, the baseline, the model performance, and the constraints, then I go and do a literature review to try and find a model that will fit within that criteria. So do all that first before going and finding the model that you're going to use. And then once I find that, then only I go and code, right? So it's the final step. When I was an undergrad like you guys, I was always in a hurry to start coding. First thing I do, I think about problem, I go and start writing code. Now, as you can see, it's the last thing that I do, right? So as you mature and you realize the mistakes you made and the problems in the systems that you built, so that's something I would also advise you all to do. Do your due diligence, do your research way before you actually start coding, selecting models, all that. Establish all this, and that will put you in the mindset of somebody who's doing production machine learning. Also remember, like I said, the differences between structured data and unstructured data. It's a bit difficult to, it's very different the way these two operate, and how you would approach running unstructured data projects versus structured data projects. And this, I'm sure, is something you've seen over and over again. You start with data, you write the algorithm, you code, you tune your hyperparameters, and then you have a model. And you keep going through this loop where you define model, code, and training, you train it, and you analyze, and you keep going around by tuning your features, your data, your hyperparameters, until you reach that performance level that you want to get right at the start. There are two main methods used for training a model in the world now. We have the two methods, which is called model-centric and data-centric. Model-centric is where your data set is fixed, and you try to improve performance on that fixed data set by either using different models or different hyperparameters. You keep tweaking the model to try and improve performance. Data-centric machine learning is where you keep your model fixed. Where, let's say, your vision model, you pick something like YOLO or something and say, right, I'm not going to go beyond YOLO. But then you try to improve the performance of your model by changing your data, by improving the data, by making changes to data. So you have two variables here that you can change. You can either, to improve model performance, you can change your data, or you can change your model. So if you try to change both at once, it gets a bit complicated because you don't know where the improvement is coming from. So normally when I do machine learning projects, I pick one of these two methods, where normally now most of the projects I do are more data centric, because it's because that's the easier way. You know where your project is going, why it's doing wrong on something. But I usually try to pick a model, don't change that model too much. And my experimentation is all about how I work with the data. I maybe add new parameters, I add new features, I create new aggregated features, I think about how I represent the features. Is it going to be a numerical value, a categorical variable, a bin number? There are different things you can do. But my normal preference now is to do most of my machine learning in a data-centric way, where I don't really play around too much with the model. I try to improve performance all through how I manipulate the data. And yeah, this just shows you a difference between model-centric and data-centric ML, where, once again, remember, model-centric ML is where the data is fixed. You have a fixed data set and you try to improve performance. by adding new models or changing your model, adding new layers to your neural network. You try different things like that. Data-centric is your model is fixed, but you try to improve performance by manipulating the data. And something very, very important is, as you can see, something I've been saying over and over again is that machine learning is an iterative process where you try one thing, you analyze it, then you go back, you make some changes to your data or your model, and you keep going through that over and over again. If you worked on a large machine learning project, you'll find that you will run hundreds, maybe even thousands of experiments like that. Now, if you take my PhD, which I did years ago, my PhD was eventually at the end of my PhD, I had run something like 25,000 experiments, different training runs on different data and all that. And if you don't manage your experiments and track your experiments well, that's once again, you won't know what's happening to your project. So that's something I would also advise you all to do whenever you all are starting on a new machine learning project. Come up with a very organized way to track your experiment. Write it down on a book, use an Excel sheet, whatever, but make sure you track your experiments. It's very, very important to do that. Then this is something that is becoming more and more important now. Model explainability, and more laws around the country, even in Sri Lanka, it will come in, not immediately, but it will come in at some point. But model explainability is a very, very important thing, which is instead of, most of the problem with machine learning is that it's a black box. People don't know when something goes in and something comes out. Why this is coming out, there is no understanding. So now there is more and more emphasis on creating machine learning models that are explainable, that will actually explain to you why it make a particular decision. If it gave a person a credit rating of, say, 50%, it should be able to explain why. What was the reasons why that person got a credit rating of 50%? And then finally, the deployment side, which is the most important part. And this is that that what I was talking about in terms of how you create a model serving infrastructure. When you have a model ready, you need to be able to put the model, you need to manage it so that something you probably understood through this talk is that the machine learning model, once you take it into production, is going to be continuously retrained all the time. So a model that's there today, tomorrow it may be retrained and there'll be a new model. Day after tomorrow, there'll be another model. So what you need is, you need some sort of method that will do version control of all the models that you trained in your system. And that has to be linked to some sort of a loader and a manager, which will then make it available to all your clients, the apps or whatever, through an API like this. And this may look very, very complicated, but there are already frameworks which do this for you. TensorFlow serving is one environment which can do this for you. But if you don't do version management of your models, once again, you won't know what's going on. And especially, let's say you retrain a new model and that doesn't perform very well, you need to roll back to the earlier one. You need to have a log of those early ones that you had as well. How do you deploy these models? Now, whenever we are replacing a normal software system with a machine learning system, or we have a good machine learning system and when we are replacing it with a new one, we don't just turn one off and turn the other one on. That's too dangerous, because most machine learning models, the first time you run them, they don't really work. They don't work very well. So what we do is we use these different methods like shadow mode, canary deployment, blue-green deployment, where what we normally do is we run the old system and the new system in parallel. We run the new system. So let's say we have 1 million customers. Let's say we have a new credit rating system that we developed to replace the old one, but I'm not really sure whether this is working well or not. So what I would do is I would first run my new system on maybe about 5% of my customers, and the remaining 95% would still be served by the old system. And then for about a week, I would run that and see whether there are any complaints, whether it's doing something wrong, and monitor it and evaluate it for about a week. If it's working well, then the week after that, I would increase that 5% to 10%. Then the week after to 15, 20, 25, like that. So normally those are the methods we use for deployment, which is don't just turn something on, off and turn this on. That's way too dangerous. Things can go wrong. So we always have these different methods, and this blue-green deployment, canary deployment, all different methods to be able to do that. Also very important, like I said, to monitor the models that you have deployed so that you know when it has gone wrong. You know it's not working very well so that you can go back and retrain it. So logging of everything that you can, from server load, memory compute, throughput, latency, drift, which I'll talk about in a bit. All these different things is very important to log these in as much detail as you can. The main challenges that we deal with, especially when we are deploying, for deploying data, deploying these machine learning systems, is there are two ways that you can look at it. You have the machine learning challenges and you have the software challenges. Machine learning challenges are three things. One is model drift, data drift, and those are really the two ones. Gradual drift and sudden shift are actually combinations of those two, which I'll talk to you about in a bit. But the software challenges are what you normally get with any type of software. How do you deal with real-time data versus batch data, running your system on the cloud versus edge versus IoT versus on a browser, computing resources, latency, logging. These are what you would normally face with any software development. But the machine learning challenges are a bit more different. This is a good example. This just shows you what this actually means. So let's say you built a classifier to classify between these two classes, the red and the yellow. And your classifier has beautifully defined this boundary. So whenever you give a new data point, depending on whether it's on the left or right of this line, it will classify it as red and yellow. But then concept drift is basically what happens when the world has changed. The situation in the world has changed. So think of it like this. So I'll give you two examples. Let's say you're building a clothing recommendation site. Let's say you're the person who recommends clothing on Amazon, where when you go in, it'll recommend items of clothing for you. And let's say you build this at the beginning of the year. Sorry, you build this, let's say, around this time of year, which is now it's just coming into spring in the US. And it's working really well. When people come in, your purchase rate, your conversion rate is running at 5, 6, 7%. But then you suddenly realize, come around June, your conversion rate is suddenly starting to go down. Why do you think that is? Because your system is still recommending spring clothes, and now it has become summer. So that means the whole world situation on what's red and what's yellow has changed. So that means your system has once the environment, society is changing from spring to summer, they have to start recommending different items. They can't recommend the same things they were doing 3 months ago. And so and then once again you go into autumn. Once again, you have to do that shift again. When you go into winter, you have to do that shift again. Another good example was, probably not many people know this, but soon after COVID hit, most of the credit card fraud detection systems in the world crashed. And for about 3 months, they were just turned off because all those people who were making 1, 2 transactions a week with their credit card, suddenly when they were in lockdown, they were making 30 transactions a week with their credit card. And then the system all suddenly started flagging saying fraudulent. This can't be that same person. The whole spending pattern has changed. So this once again is a concept drift where the world situation has changed. And then the mapping, what was earlier detected as a fraudulent person is no longer a fraudulent person. That's somebody actually doing things correctly. But the system is now detecting that person as fraudulent. So these are the type of things that are very, very difficult to monitor and track. But then that's the challenge of building a production machine learning system. So this is a good example. So let's say you build a model where you build this catapult to shoot these balls into this basket here. A data drift is when suddenly these balls are suddenly made a bit heavier. So that same bit of force that you tried to use earlier, when you try to shoot it, that force, it doesn't get to the ball. So that means the initial data, the data that's being fed into the system has somehow changed. It has drifted. Something in the world has changed where this data has changed. And the concept drift is more to do with the actual goal, what you're trying to map to, changing. So in this situation, the balls are still going to the correct place, but now the basket is in a different place. It's like going from autumn to summer, right? So where the whole thing has changed. So these are quite advanced topics which we can talk about in a lot of detail, and this probably dealing with things like data drift and concept drift are university courses on their own. They are very wide scope, but this is just to give you a general idea of what it is. But these are the type of problems that we face every day as machine learning engineers, because the world is always changing. So on our side, the challenge is how to detect this, and then once we detect them, what are the actions we need to take to get the model again back to performing where we wanted it to be performing. Then testing machine learning systems, once again, is very hard. It's a lot more challenging because with normal software systems, you have code, you have unit tests, then you have integration tests, and when the system is running, you test it. But when you're talking about machine learning systems, there are so many different aspects that you need to test. Just like normal, you need to test the code with unit tests and integration tests. But then you have your model training, you have the model tests, and you have to test for data tests, queue tests, data monitoring, prediction monitoring. So actually, monitoring production-grade machine learning systems is a lot more complex than monitoring normal software systems. Yeah, I think we can go through this. So this is basically the end of my talk, which is just to explain to you that AI and machine learning is no longer a scientific domain anymore, right? It's a real engineering domain now. We're actually trying to use machine learning and data science to help people, to actually make a difference in their lives. And industry really at the moment, the biggest demand within the machine learning space now is for production engineers, people who know how to take these models out of your laptop and into people's hands to actually help people. And for that, everything I talked to you about today is about how to build those ecosystems, how to build those larger systems so that you actually build something that will be immediately useful for people, but it will also continue to be useful for years to come because the system can be managed and updated as you go along. Right? So I think we have a little bit of time for questions.
Doctor, shall we start with a couple of questions that are put online? One is there any specific procedure to ensure the privacy and security of the data during the model training and deployment process?
There's no specific procedure. I mean, you've got to, there are methods like dehashing, hashing of personal identifiable information. But a good rule of thumb is that a machine learning model should never contain personal information. What we also do at Dialog is we have maybe segments or personas. We break people up into personas, and we may train a machine learning model on a persona, but we would never train a machine learning model on a particular person's name or address or telephone number, things like that. And that's the responsibility once again of a data scientist, to make sure that you strip off any personal identifiable information, PII data, from your training, and that is not followed everywhere, and that's a compliance. But there are new laws coming into Sri Lanka, the Data Protection Act, which is coming to Sri Lanka. It's already enforced, but they haven't started enforcing it yet. But this will be law in Sri Lanka very soon as well. But machine learning models should never contain, training data should never contain personally identifiable information. So it's the responsibility of a data scientist to strip all that out before actually calling these models.
Thank you, Doctor.
Yeah.
There are a couple more questions online, and if anyone has questions in the audience, I can pass the mic around as well. So the next question is, what are the steps to monitor and diagnose the behavior of models in real time? And how can we trigger alerts or notifications when the models encounter unexpected or abnormal situations?
Good question. So, the whole number of things that we monitor for. And it's usually monitoring would be very dependent on the type of application you're running. A vision application versus a speech application versus a recommendation system is fundamentally different. But if I was to put it together, what we normally monitor for is data drift. Try to see whether the incoming data, anything is changing in that data. And what we normally do is at the start when the system is running, we collect some statistics on the data. What are the distributions? What is the min, the max, and things like that. And we monitor those statistics in real time. Every 5 minutes or 10 minutes, we look at those numbers of the current bit of data. And if you see that any one of those metrics has changed, then we know that the data has drifted in some way. So that's one. And then the second one is concept drift, the mapping from that data into some sort of action. And if we find that more customers are rejecting the actions that we are proposing, that once again means that there's been some sort of a concept drift going on. Similarly, we would also monitor things like model usage, the data, how many null values are coming in, what's the data. But really, it's very reactive the way we do these things. We would do some simple ones for data drift, concept drift, but then as we see more and more problems coming in, we add another module to monitor for that as well. So it's a continuous process. We are adding more and more monitoring modules as that application progresses. Yeah?
There's another question. How can we quantify the impact of data drifting on model performance, and what are some key metrics that we should track to monitor and mitigate this risk?
I mean, the key metrics are usually it's very difficult to quantify it, but key metrics are, like I said, we look at normal distributions of the data. Because data is usually a whole lot of features, and what we do is we would monitor the distributions of each feature. Like what are the min, the max, the average, the norm. What we do is we take chunks of data at different times, and we calculate those statistics and we save it. Then 5 minutes later, we calculate those same statistics and see whether they're the same. So they really should be the same. But if it has shifted by a large amount, then we know a data drift has happened. So it's really more statistic generated, but it's also very context dependent. It depends on the application. Images, for example, image processing is totally different. What we then do is look at like the color distribution of the image. Suddenly, if there's more white in an image, then maybe the camera is broken or something like that. Right? So there are so many different ways that can happen. The source may go down, the data source may go down, the data source may be hacked by somebody, or there's some electrical problem, the connection problem. So you got to build it so that you can detect all these different types of changes on the source side, so that you know that when that source has changed, your model is no longer going to perform. So that's why depending on where your data is coming from and what type of data, you got to visualize what can go wrong and then build mechanisms to monitor for that.
There's another little bit of a different question from Amri Zamin. It says, hello, Dr. Romesh. Apologies as for the question isn't entirely about today's topic, but rather needing advice to mold my career around AI. I'm currently a student majoring in accounting and finance. Since my field is entirely different from AI, I would like to hear your suggestions on how I can put myself into such a pathway requiring these qualifications.
It's a lot easier than it used to be, especially within accountancy and management. I mean, AI is the future, and what I would suggest is first learn the applications of these. What they're actually being used for. And now there are so many different low-code and no-code tools which are coming out in the market, where you can actually build these systems and deploy with almost no coding knowledge. So you can, one good example is a platform called KNIME, K-N-I-M-E, which allows you to build almost any type of machine learning system you want with no coding. So what I would suggest is start with understanding what these systems can do and try to put some of them together with these low-code and no-code tools. And that will give him an understanding of what's the potential. And then once he finds some of those of being an interest, then he can do a bit more of a deep dive and try to understand how you can code one of those yourselves. But I think for somebody like that, it's probably better to start at the application level and then move downwards start digging in more on the technical side. But first work on application and then go into the technical side as and when he needs to.
All right, Thank you, Doctor. In the audience, is there anyone who has a question? Just
first of all, I must express our appreciation to Dr. Romesh for giving this excellent presentation on machine learning. And actually, I have been communicating with him on the same topic for many, I would say, years. My question is like, I have two questions. The first one is that when you look at our university system, in all computing degree programs in the second year, we have something called this industry-based software project or software engineering project or whatever. Basically, in all the places we are encouraging students to go through the software development life cycle and develop industry appreciable software. So then by that time, students have already done software engineering, then the programming, databases, system analysis and design, and that kind networking, that kind of knowledge is there with the students, so therefore they can apply that knowledge. But when you take our student here, so actually their situation, what we call it, AI based software engineering project actually. So then we want to use the AI techniques in that project. So then can you give us some ideas in which way we can extend the second year project with the machine learning ideas and so on?
The main thing is for students to be, for them, the idea of a machine learning project to change from taking a data set and building a model and showing accuracy on the model. I think the benchmark should be where as much of these projects as possible should be made into something that can be accessed by other people. A web portal, a website, an app.
Yes.
And that should be the minimum benchmark. So lot of the projects I've seen in universities where they just do a small POC and maybe even like an IoT application where they get a robot moving around. But the moment you ask them to change something, it will take them 3-4 months. So if they can work on that larger application, but also think about how they're going to modify this going forward, build these whole MLOps pipelines and all that. If those can be the minimum benchmarks for these projects, I think that will take them a long way where they need to be.
Actually, do you think that we are going to operate as a group project? So then about 4 to 5 students are there.
Yes.
So I think that mode would be much better than individuals for the second year.
Exactly. I think that will be perfect. I mean, it's more that benchmark we set for what is an acceptable project and what's not. I think we need to move to the point where we say taking a data set and training model is not good enough. And move it beyond that.
Okay.
Yeah?
So then at the time we formulate the project, we'll contact with them.
For sure.
Okay? Definitely. And you can also supervise our projects then.
Of course.
Yes. I have one more question actually. Now when you take up this explainable AI part into machine learning, so then in all the general ML solution now that part is practiced or
it's becoming it has become law in Europe now. If any system in production has to be explainable. Recommendation systems, credit scoring systems. In the US and all, in Europe, the new EU laws were passed for Google and Facebook now. If they recommend a Facebook post to you, you can go. You have the right to go and ask them, why did you recommend this to me? And the AI should be able to explain it.
Okay.
So now it's probably one of the most active areas of research because now it's part of law. So it has to be. It's not perfect still. Companies are trying to get away, but there is a lot of work going on this to do that. Now even vision, there are more and more algorithms coming out which actually show you which part of the image the algorithm used to make that classification. So like that, there are more and more systems coming out, but it's a very, very active area of research now, especially because it's law. Companies don't do things unless they have to know. So, but now, because it's law, they have no choice.
Okay, thank you very much.
No problem.
Are there any other questions? Anyone?
Machine learning, there you go.
Yes, sir. So it's actually a small question. Uh, so we are very beginners to this field. So my question is actually, sir, you told many technologies and many frameworks used in this field today. So actually we learned many things. We It's very valuable for us as a batch and as a degree as students. So my question is, what are the uh, main you told many frameworks and many technologies like AWS uh, and many frameworks like YOLO and like that. So what are the main things to learn as beginners for us?
So, I mean, it really depends on the type of application that you're building now. In vision, this is a field that's changing really fast, and now this was something I was questioning myself. Now, all this time, the main thing is learning how for vision how convolutional neural networks are working. And first, when you would start, I would say use some of the models that are already built by other people, YOLO, ResNet, Inception. There's models. There's something called the TensorFlow Zoo. You can go to TensorFlow Zoo and all the different models. There are about 50 different models that are available there, which is great. But then now, with GPT-4 coming out, GPT-4 can recognize any image and understand. So then the question comes, maybe that's not the future anymore. Maybe these generative models are the future now, because it can understand anything. It can not only understand the objects, it understands the relationship between the objects, is able to explain it, and that's the final application. So I think definitely start off with the two frameworks are probably the two best ones are TensorFlow and PyTorch. They're the best for image processing, and both of them run most of the models, YOLO, Inception, all these things. There are some new AI generated models called Efficient Det. There's it's a sequence of models which are quite good, and you can try, but there are about 30 or 40 different models. Some of them are big, small. You have to the thing is, the big models, the accuracy is very high, but you need very powerful machines to run them. The small models are very fast, but the accuracy is not so great. So you need to come up with that balance on where you're running your systems, how much money you have for your GPUs and all these different things. So I think the first step is to understand how that balance works on network size versus accuracy, and how much training data you need and all these things. And then how to prepare your training data set. Frameworks, TensorFlow, PyTorch, I think you can't go beyond that. But also AWS and GCP and Azure also have their own image processing pipelines and frameworks as well.
Yes, sir.
Okay.
Yes, sir. Thank you so much.
Okay.
There's another question. The success factor of almost all breakthrough API solutions is continuous training, real-time and automated, and open a beta version for a larger community. Gain high interaction and inputs for improvements. What are the options to accommodate / invest for local AI use cases to meet those objectives and overcome the needs of resources to work in a robust and scalable environment?
Interesting question. You still need resources. I mean, that's still the big blocker for all machine learning systems. You need compute resources. It's like a rich and poor divide now that's going on, which is why a lot of the really cool research in AI is still happening in the big tech companies. They have money, whereas the universities don't have. I mean, training GPT-4, GPT-3, one training run used to cost $5 million, which even the Sri Lankan economy can't afford that at the moment. But now with I was testing out GPT-4 last week, and it's working really well on single-is. And these models now can be okay. I don't know if you all know this, but with machine learning models, there are two ways to train them. One is to train it from scratch, and that usually takes a lot of resources, takes a lot of data. But there's also something called transfer learning, where you first get it trained on some larger data set, and you can then run a very small bit of training on your own bit of data, which is much less intensive. And that's a lot cheaper way to, and you do a lot with these vision models and things like that. So transfer learning is one way where you can train some pretty powerful models without spending lots of resources. And even these new OpenAI ChatGPT ones have a transfer learning sort of interface called fine tuning. And fine tuning, instead of spending $5 million, you can probably train on a little bit of your own data for about $10, $20. So there are ways, but I think if you want to do it at low cost, probably transfer learning is the way to go.
The next question is, when it comes to big data, how can we scale the data set to the NLP, ML models to optimize the real time of the training?
That depends on the application you're going to go and how the data is labeled. How the data is labeled, and there are a lot of factors. It all depends on the application. Optimizing, I mean, that's all about how you create the pipelines, how you create your libraries to process, pre-process, all that. Real time, it won't be real time training. You'll probably train once a day, once an hour, or something like that. So there'll be something sort of triggering which goes on. But it's not going to be always learning and always training. There's going to be some system that's going to get triggered and cause the retraining. But in terms of optimizing, it's all about how you code, how you manage your libraries and your arrays and all that stuff. Yeah.
There's one more question. How do you handle a data breach should it happen?
With great care. Yeah, I mean that's always. I mean that's not only for machine learning system. That's for any type of software system. If you have a data breach, how you deal with it is it depends on the severity of the breach and what type of data and the legal ramifications. But machine learning data breaches are no different to any other normal type of data breach.
All right, thank you so much, Doctor. With that, if there's any other questions in the audience? No? Okay. With that, we can conclude. Thank you so much, Dr. Romesh, for taking time out of your busy schedule to be here with us and impart your wisdom on production machine learning to all of us here today. I'd also like to thank Professor Karunananda and Dr. Tushari for helping us coordinate and make this event a success. The team at papre.lk, thank you for helping us set up this live stream. And to all of you in attendance, both physically and virtually, a big thank you to all of you. I'd also like to invite Yasiru Markovita from the team at PSI to talk about one of our upcoming projects.
Good afternoon, guys. Once again, thank you very much, Dr. Romesh, for the valuable session. I hope you all got something out of this, because you will see the value of this session, not right now, maybe in a few years when you step into the industry. Because like Dr. Romesh mentioned, the industry look at things very differently than how academics does. We felt that transition when we came here, the challenges. So if you adapt these changes, look at overall pipelines like Dr. Romesh mentioned, and change your projects and change your skill sets accordingly, the transition into the academic, from the academics into the industry will be much more easier for you guys. One reason, I know in universities you all develop very cool technologies, cool projects, but we see, working with the universities for the last couple of years, we see that most of these cool projects and piece of technologies die at universities. You leave them at universities and come to the industry. One reason is that they are not adaptive to the industrial environments. The real world application of those technologies is not practical. So to help you guys bring those technologies, those cool projects into real world, we have come up with the project. It's kind of a competition. We call it for now the Dialog Visual Innovation Competition. It's going to come out in May, the first week of May most probably. It's a 6 months long program, kind of like an incubation program. So you can give us whatever the projects in IR 4.0 domains, which you have already done or which you are planning to do, submit it to us. We'll evaluate them, and then we'll guide you how to develop those projects into real world applicable programs. So there will be several stages in this competition. Initial idea shortlisting, semi-finals and finals. During all those stages, like we'll have this kind of engagement sessions like Dr. Romesh did, much more different arenas. So we'll help you to groom your ideas, not just in technology fields, but in finance side, business side, and all those, and we'll help you develop a prototype if you need, and then we'll have a grand finals. So we'll have a huge prize pool there, actually a 5 million prize pool for the finalist, and then that will not be the end. We will introduce you to a pool of venture capitals. So what we're going to do is, the finalists can pitch you refined ideas into a panel where they are ready to invest in you. If your idea is good enough, your plans are good enough, they will help you go into the market as a startup or a company. So you can keep coming up with ideas, think of different technologies you can introduce into our competition. And I hope to see you, most of you, in May. And thank you very much once again for joining with us today, and hope to see you all again in another session. Thank you very much.